week, we are absolutely delighted to be joined by Dr. Nagar Khorasani, who is at the University of Buffalo. She's an associate professor in the Department of Civil, Structural, and Environmental Engineering, and is really focused on understanding the performance-based design and resilience of structures and communities under extreme hazards, including fire, the thing that we are all interested in here today. And she has an impressive resume in addition to her very impressive work. She's a recent recipient of the AISC Early Career Faculty Award and last year's recipient of the National Fire Protection Association's Fire Protection Research Foundation Medal. So today she'll be talking about some of her research and I want to give her as much time as possible. So I will let her take it away. Thank you for being with us, Nagar.
Thank you. So let me quickly share my screen and I think it should be good. There you go. So thank you, Dr. Golden, for the introduction. Thank you, the California Fire Science Seminar Series, for the invitation. It's a pleasure for me to give this seminar, and I would be more than happy to have a discussion afterwards in terms of some of the research needs and where we're going with this kind of work. So hello everyone, the audience. Thanks for attending this seminar. And today I'll be presenting on structural damage from wildfires in wildland-urban interface communities. So in terms of motivation, I will keep it short because I think on this call we all agree about the need and urgency to better understand the behavior of wildfires when they reach communities. Wildfires have always been part of the natural landscape and they are needed for a healthy ecosystem, but these fires are projected to become more frequent and intense because of changing weather patterns and anthropogenic activities. So for example, in California, we've had the 12 out of 20 largest fires since 2017. And again, 12 out of 20 most destructive fires since 2017. And every year, the list gets updated with more events. So the existing wildfire risk assessment procedures rely primarily on exposure and historical data to prioritize wildland-urban interface communities without really explicitly simulating the community response. So if we had such a tool that we could simulate community response, we could guide response in terms of whether the fire is moving too fast to be suppressed or whether it would be, where would be an optimum location to attack the fire during the event. We could also use that kind of tool for mitigation to identify vulnerable parts of the community. So I'm going to play a video. It's just a minute, and it's from the Marshall Fire that happened in Boulder County in Colorado, and that was last December. It was December 2021, and this fire was less of a, I would say, wildfire, and it was more of an urban fire given how close the fire started and reached the community. Okay.
And this is the situation where, you know, one house is burning and the whole thing's on fire. And because the whole thing's on fire and the wind's blowing, then parts of it and embers and smoke and flames and everything are all burning around the neighborhood. And then the next house is on fire. The Marshall Fire moved so fast. We had to determine whether or not we could do anything to the house with the time that we had, which was minutes.
Cherryville Command, I have you with 5 resources at this point. Do you need more help out there?
Definitely, we were met with the most challenging fire environment any of us had ever seen. The worst part, we call it triage. So there was homes that were already beyond saving, but we were able to find that line in the sand basically, and found a place where we could safely engage. We had a good water supply, and we had enough resources to make a stand on many, many homes with aggressive firefighting and structure protection.
Okay, so what we are after basically is quantitative assessment of vulnerabilities and the drivers of loss in communities, we can then adjust and recommend guidelines to reduce losses to either acceptable or tolerable thresholds. We know, from this figure on the right, we know there are certain activities that we can do to reduce the vulnerability. We know increasing the distance between the buildings would help with reducing the chance of fire spread. What should that distance be? 30 feet, 100 feet, or how does that influence the fire spread in a quantitative way? We don't really know all the details. There are other things like management of fuel breaks close to the communities, using fire-resistant materials and features of every structure, vegetations around buildings, and so on. So it is important to be able to evaluate the effect of different mitigation actions, including fire resilient construction, defensible spaces, and a combination of them, not just single activity, but a combination of them on how those would reduce wildfire losses for a specific community. So in order to get there, we're going to go step by step. So the short-term objective is to capture the spatial and temporal behavior of wildfire inside wildland-urban interface communities, considering the features of that community. So before we get into the main part of the presentation, I want to briefly discuss what we can learn from the data. So what data shows us in terms of structural vulnerability and some of the not drawbacks, but what we can get out of a data-driven approach versus when we rely on data versus switching to a model that doesn't purely rely on data, and that might work better for our purpose. So, okay, I'm sure many of you again here on this call, you're familiar with the Dean's data set. This is basically a data set by CAL FIRE on damage inspections after events, wildfire events, and it includes information on more than 76,000 structures from number of events, about 150 events, and it goes time span of 2013 to 2020. The information includes detailed structure features. Is intended to include such as window types, roof type, whether or not the structure fences are attached, and so on, lots of details. But some of the earlier events back in 2013-14, they're focused more on recording information for damaged structures only. That is, we actually don't have information for those houses that survived the fire, which makes it a little bit hard for actual vulnerability assessment. So we found detailed information about some wildfire events and the community characteristics that are listed here. These are 10 events. They're all post 2017. And when I say details, we use publicly available sources. So those include CAL FIRE, MTBS program, elevation information, and land fire, or basically type of land surface fuels we have up. And I'll explain in detail in the next 2 slides what we have done. But one issue, again, I'm going to upfront mention that is that most of these events, of the 10 that we have here, these are extreme events. For example, the Campfire 2018. That's a large number of structures, and that's good, but pretty much almost all of them, or major portion of those structures, burned down. So it makes it hard, again, to make some conclusions based on the data. So what was the purpose? What was the approach here? The aim is to look at the effect of several parameters related to hazard and features around the structure on the level of structural damage. So pointing out the analysis being done at the structure level, and we lumped the damage categories from Dean's data. So the Dean's data set tells us what was the level of damage. We are actually looking at a binary output to simplify this. So damaged or not damaged, to make the process easier. So the parameters I will be talking about include hazard and, again, features. So for hazard, we have separation from location of ignition. And I am not calling it distance, I'm calling it more of a separation. Why? Because this is now just a sample plot. We have the final fire perimeter. Here's the ignition, location of ignition, and here's a structure. So all these little dots that are shown in gray, these are basically structures from Dean's data. This is a given structure and it is outside of the perimeter, that's okay, but it was inspected. So this structure, when we are looking at a separation from location of ignition, we are actually including the distance between the structure and ignition point and the perpendicular distance from the structure to the line of direction of fire spread. How is that line defined? That line is going through the ignition and through the centroid of the fire perimeter. We are also using burn severity maps to characterize the hazard. I'll talk about them a little bit more in the next slide, but basically fire severity is being calculated upstream of the structure. When I say upstream, what do I mean by that? Well, we did a little bit of a involving like geometry. There is no conventional approach widely accepted to define what would be the area of the influence on that structure. So if this method is the best method, not necessarily, but we used it consistently for other parameters such as land cover upstream, that we needed some sort of a reflection on the area of influence on that structure. So if that's the structure, here's the ignition, here's again the final perimeter. We draw a circle first. That's going through, center is the ignition point and it's going through the structure. So the pink area is, upstream of the structure. Anything that's outside of that circle definitely will not affect that structure. That structure is, the wildfire has already crossed that point. But this is probably too large, areas up here, when it's burning, it's not going to affect that structure. So let's continue. Let's draw another circle. Again, lots of geometry, but this new circle is still going through the center, is the ignition, location of ignition, but it's going through the centroid. This green dot is the centroid of that new pink area, which is giving us this purplish or darker pink. And that is going to be the segment of influence for us. And when we are calculating fire severity or land cover upstream of the structure, it's actually the weighted average of the values within that segment of influence. And this is being defined per structure. For any given structure, the process is repeated to get the segment of influence. The other parameters we've included is the number of neighboring structures, topographic position index, and the land cover upstream of the structure. And I will talk about them again on the next slide. So this is a sample of results. We're just looking here at the influence of hazard. So we have separation from location of ignition and fire severity. Here, these are the probability density functions, PDFs. And red these are the damaged, and green, they are the not damaged. So what you see here, these are absolute values in terms of distance. What you would see here is that you have a little bit of more data points. The histogram is a little bit larger for damaged structures when you're at a closer distance to the location of ignition, and you have less, so the red falls below the green being not damaged when you arrive at distances or separation from location of ignition. With the severity, it's the other way around, in a sense that when you have more severity, fire severity, which is again coming from the MTBS maps, a weighted average on the segment of influence, once that value increases, the histogram for damaged structures tend to be larger than the not damaged structures. Okay, so kind of see the process. We have all these we generated similar PDFs for all the other parameters. And then let's look at a different way of results. Now, in this plot, the x-axis, again, is the parameter of study, and the y-axis is the standardized value What do I mean by standardized? It means basically you got the histogram from the previous slide for the parameters under study. Then for each observed value of the variable, you subtract the mean and divide by the standard deviation. That's why the values are around 0. So we are looking at box plots here. And for the sake of discussion, right now let's look at the median values. The median values are these black bars that basically are shown for damaged and not damaged, red being damaged, green being not damaged. So separation from location of ignition. Want to again reflect, it basically mimics the time that it takes. We are not looking at fire spread, it mimics the time that it takes for the fire to reach the structure of interest. And fire severity is basically is a proxy for that intensity of the fire that's perceived by the structure. So there's a slightly higher likelihood of not damaged structures with larger separation and smaller fire severity, which we saw in the previous slide. So we're going to do the same for the other parameters. The next one is the number of neighboring structures, and we are looking at that number in and around the structure within 30 meters, 60 meters, 90 meters, 180 meters, and 540. So we're keep increasing. There is somewhat a trend for sure that with smaller number of neighboring structures around that particular structure under study, you would get less likelihood of damage. When you have more structures in the neighborhood, you have more damage. Next parameter is TPI, which is basically calculated. It compares the elevation of each location with its surrounding. So it's basically a focal index. So a large positive value is it's a higher ground, like a hill, and a large negative value is a much lower ground like a valley. And TPI we calculated for each structure considering two window sizes. One is, you see, 100 and the other one's 1,000 meters. And again, houses with a positive TPI is on the higher ground. And again, we see it's not completely clear, but perhaps just a little bit of a higher ground could see somewhat in the data that is maybe here you have the red a little bit higher than green within the 1,000 meter in the window, gets a little bit more damaged. Okay, and then the next one is the land cover. So the land cover upstream of the structure was calculated for 5 categories. These are the non-combustible, crop, tree, shrub, and herb. And it's harder to see a complete trend here, but I would point out that this is cumulative in the sense that if an area has more non-combustible perhaps around the structure, you might get less of the other categories. At the end of the day, it had to add up to 1. But there's definitely on non-combustible, it's easier to see how you would get for larger value of non-combustible land, you have more damage. And the hypothesis is that an area with higher density of structures, again, going back to the neighbor, number of neighbors, the area with higher density of structures could also have a higher portion of non-combustible category, meaning you've got roads, parking lots, and driveways, and so on. So at the end of the day, looking at this plot, where I started, we want quantitative assessment, right? So comparing the median values, we kind of see that the median for the separation to location of ignition is larger for not damaged structures. The median for fire severity, number of neighboring structures, TPI, and non-combustible land are larger for damaged structures. And these make sense, again, knowing what we know. We even went one step further and fit this data to arrive at the logistic function for the probability of damaged structures, sort of a binary 0 and 1. But the issue is that we need more data for a robust assessment, especially data on milder wildfire cases where structures could survive or not, to make this pure data-driven model in a way that we can rely on absolute values rather than comparison, because I think this is more suitable at this stage for comparing values, not necessarily relying on the absolute probabilistic values. So with that, shifting gears in the presentation, now I want to talk about how we can go deeper and capture some of the physics of the problem, maybe combine it with the data, but we'll see what we can do at the WUI level. We have fire spread going on when the wildfire approaches or reaches a community. And fire spread basically follows different mechanisms, and they're similar in wildland inside communities. Obviously, I'm more focused inside communities on this slide, but we have direct flame contact, the first one, the left. And that's when you have the flame moving and touching the surface of the building, causing fire spread. Then we have radiation, which is basically heat moving through space as energy waves. And we have convection. Convection is heat through hot masses of air, and convection and flame contact, this one, the first one, the last one, some extent also radiation. They get affected by wind, direction of the wind and wind speed. And the last mechanism is fire spotting, which is basically burning embers that are transported over large distances. And this one is a significant contributor to fire spread within WUIs, and the embers can arrive from the wildland or from the houses, both. So as the houses are closer to the vegetation, they get affected by embers coming from the wildland. If it's more of an urban area, then structures can also produce embers and affect the other structures. The process that's involved in fire spotting include firebrand generation, transport, and then landing and causing ignition. So the number of firebrands generated and their size distribution also depend on the type of fuel. So again, trees versus houses. And then the distance they're carried over depends on their size and wind speed. So we still need to consider wind again when we're looking at fire spotting. So considering all these mechanisms, we have developed a code to capture fire spread within a community, and we're calling it SWIFT, which is Streamlined Wildland-Urban Interface Fire Tracing. There are currently 3 types of fuel defined in the code. This is a work in progress, so we are expanding. There are elements for sure that we are working on to expand, but right now we have 3 fuel types: structures, vegetation, and non-combustible. And the non-combustible again includes roadways, ponds, and so on. So let's say we have a few cells ignited at the beginning, and the fire propagates based on radiation and fire spotting, perhaps the most 2 important ones in WUI areas. We also have a prompt in the code. I want to make sure, there's no direct flame contact, but we do have a prompt in the code that once the structure is on fire, just one cell of a structure, so a structure can be made of multiple cells given the resolution of the model, the fire spreads within the structure gradually, so internally. That is when, again, a cell catches on fire because of radiation or spotting, doesn't matter. We're not going to wait until the rest of that structure also experiences radiation or spotting from outside, but internally the fire would spread within the structure over time. So we get, again, some ignited structure cells or vegetation cells. We do have different phases of fire: developing, fully developed, and then cooling. For vegetation cells, we have burning and burnout, completely cool down. So the spread mechanisms, spotting and radiation from structures and spotting from vegetation, they're active when the structure is fully developed, the fire is fully developed, sorry, and then the vegetation cell is also fully burning. So once they're cooling down or they're just developing, there will not be a mechanism from those cells to spread the fire. And the last thing is the ignition criteria. So the ignition thresholds are set based on the total accumulated energy due to radiation or the number of firebrands landed on a surface, which is also related to the mass. So there's that relationship built inside the code. The spatial resolution of the model is 10 meters, and the model updates every 5 minutes. I want to, again, overall philosophy, just a quick pause. Here, I started with looking at the data, and I made this statement that that probably is not the best approach. So the overall philosophy here is to combine some theory and physics, what we know, with observations and experiments, data from experiments, and knowing the uncertainty in the process includes some probabilistic approach in the framework. This way, we basically, just to give an example, the radiation follows the physics, but spotting is really hard to capture all the steps within fire spotting through the theory or physics of the problem. So we rely on some data-driven models. And at the end, it gets us that fire spread model. One more slide in terms of background, and then we'll get a little bit into the results section. So I mentioned that fire spotting has multiple phases, and I did here mention, so far I talked maybe more towards the bottom. Now I want to quickly talk about the probabilistic aspect. This process, everything is so uncertain. So there are parameters in the model that are defined probabilistically. So fire spotting, for example, that has large uncertainty. The generation phase provides the number of firebrands generated from both structures and vegetation. So any parameter on the slide that's shown in yellow basically is a probable or a random variable in our simulation, and there's a distribution assigned to it. And we got the distributions mainly from the data in the literature and experiments. So the transport mechanism is a function of wind speed and follows log normal and normal distributions for downwind and sidewind directions. So there are two distributions attached to it. The firebrands randomly land on a cell, and finally is a threshold on the accumulated number of firebrands. So that is also not a single value. Radiation calculates basically the receiving heat flux at a location and considers the configuration of that heat source and the receiving surface, and that threshold is again a random value. Okay, so now let's talk about how this works. In terms of the input, we would need the footprint of the community. So here's a satellite image of a community converted to an input. So this is an input basically for Swift. Green basically shows vegetation. Red in this plot, these are houses, and gray is uncombustible, basically anything uncombustible. And we also get average wind speed as an input. We should put an average wind speed as an input, wind gust, and wind direction. And there is a chance between, more chance obviously on average wind speed, and then some randomly again at some points it brings in wind gust for some time steps. So I'm going to show two case studies. So we applied this two case studies. The left one is the Trails community in California that was affected by the Wish and Gojito fires in 2007. And then we have the Fountain Grove community as part of Santa Rosa in the 2017 Tubbs fire. The two communities, I'm presenting them is by purpose, their selection, because they're different communities in terms of both layout and how they responded to these two fires. So the left one, Trails community, actually the firefighters managed to stop the fire. Fountain Grove, it was very, let's say, fast fire that went through and pretty much burned all these structures within Fountain Grove. We also have, I didn't mention this, but just quickly, we also have to define the fire line at the, like once it's entering the community, or it's basically the initial ignition raster at time 0 for this code to work, in a sense that this can be linked to, if you have a other tool that basically gives the fire line inside the wildland, and it kind of stops when it gets to the community, well, you can take that and put that as an initial input to this code and then let it continue. Okay, here's the result of one simulation. I'm gonna get to thousands of simulations, just one simulation for the Trails community. So yellow means something that's ignited, red means these are fully developed, so it gets to the point that it's fully developed inside the structure. These are burned vegetation, and we can see the progression of fire. Sometimes the fire you see jumps. When it jumps, it's definitely because of fire spotting. And the fire is moving towards southwest in this case. And here is a comparison. This is the end. This is 5:30 local time, 5:30 from observation. This is from study after the event by NIST. And it's a report from the report. And they're not exactly similar, and we don't expect them to be exactly similar, again, given the uncertainties, but we definitely the pattern for this one, again, simulation randomly selected, it does capture the pattern. Let's look at also one more thing from the code. We can indeed get the result basically differentiated in terms of what caused ignition within the structure. So due to fire spotting or due to radiation. And in this case, for sure, from the beginning, fire spotting, the black line, red is radiation. The black line, we're getting more number of structures ignited due to spotting other than radiation. Okay, so here's the same simulation result, but one case for Fountain Grove. This is, again, as I mentioned, a different type of fire. Fire destroyed the whole community. The responders could not attack the fire considering the rate of spread. And what happens here is that the ignition, basically due to spotting, gonna let it run. Let me go back and maybe start over. Okay, so here it jumps. We don't have structures yet. We have more of a vegetation. Now we have these structures. We also get these structures that are now being ignited, and then these structures, the fire line. But then what happens that so once the spotting causes some ignitions and moves the fire line, then we have nearby structures of the ignited ones start also on fire, which is because of radiation. So this is a comparison of, again, what happened in reality on the right, observed, versus what the simulation is saying at local time 4:30. At 4:30 in the observation, it basically says that all of these, well, this figure on the right says these structures were all burned down, okay. What we see in the model is that at that same time, we have the fire line outside, it's left the community, and we still have a few of the structures in the ignited category, and the rest are still fully developed in the sense that they are burning, which makes sense because in reality, these fires are not, structure fire is not too quick. It's not a matter of minutes, matter of hours. They burn for hours. So the simulation is still able to capture what happened in reality. But here's the difference between, the previous case versus this one. And you can see that at the beginning is fire spotting, the black line, that's causing more number of ignitions. After some point is radiation that's taking over because the structures are really close and causing the fire to spread. Okay, so we looked at single, basically event, single simulation results. Now I want to basically show results, assuming that we run many simulations. And in this case, thousands of simulations. So what we are looking at cumulative distribution function, or CDF, of the number of structures burned over time. So we have each one of these CDF functions. It's 30 minutes, 60 minutes, 90, 120, 150, and 180. And what we see here, this is for Trails community for the first case. And we can see that there's not much spread in the first 60 minutes, basically zero. This is not really moving. So the median is sitting at the zeros. When I say the median, like looking at probability 0.5, coming down, I'm looking at a value of 0. So at 30 and 60, nothing, and then it picks up eventually. So the slower rate of fire spread explains the successful suppression operation at the time that it happened. At 180 minutes, this is the last simulation time, we have a median of about 73. So again, if I go 0.5, and I'm looking at the black line, which is 180 minutes, it's about, can't read, but it's about 73 ignited structures. In reality, and the mean was 40, max 180. Reality, the count is 90. So this is, again, reasonable, and the probabilistic approach is giving us a sense of how this fire could, how this basically approaching fire line with the wind velocity and direction and so on could affect the community. We would get this similar type of plots for spotting and radiation in terms of this, the type of ignitions caused. Now let's look at same plot but for Fountain Grove. So we have CDFs, and this time 30 minutes is not sitting at 0. There's actually, you know, it's actually a wide range minimum maximum, meaning that some of these scenarios or simulated cases are so aggressive that they pick up so slowly. So we have a median of 157 with mean of 80. So I'm looking at the red line at 120 minutes, about 80 to about 180 with a median of 157, about 160, where in reality, we don't have an exact count, but it's about, it says approximately less than 200 structures. So we are definitely, our maximum is more of what happened in reality. So from the simulation, one of the extreme events, one of the extreme cases actually happened in reality. So that it also explains why they were not able to suppress the fire, or didn't actually try to suppress that fire in at the time. Okay, so that's the type of information we can get from the model. Now I want to go back to the discussion we had at the beginning of the presentation, and how we would need to quantify the effect of parameters that we know they're important and could influence the response of the community. So NIST has recently published an extensive study, a thorough study on WUI structures and fire hazard mitigation. And within that report, they're suggesting the definition of WUI, you know, should include the structure separation distance, call it SSD, structure separation distance. And they're categorizing different WUI types, basically based on SSD, parcel size, and housing density. Given the fact that within the field, within historic events, we see the importance of structure separation distance on the survival of the structure. So we completely agree on that. But the question is that, okay, how, again, can we have some quantitative assessment of how these, for example, 3 cases, and I'm highlighting them in yellow, 6 to 30, 30 to 100, and above 100. And I'm looking at basically the interface. Doesn't matter, you know, perimeter versus interior, but you see on the next slide, we are basically looking at high density, medium density, and low density communities. And that our cases mapping to the highlighted yellow ones in the table, we have 18, which is between 6 to 30, 65 between 30 to 100 feet, and 100, which is just borderline for this case. And our parcel size and housing density, the housing density basically goes down low density, high density. Okay. So we simulated these 3 cases using Swift. There are other inputs important, for example, wind. We picked what I'm going to show here, basically, for considering the time. Just one scenario where the wind velocity is similar to the Witch and Gojito fire case, so the trails community, so that eventually we compare that with that realistic case and where we stand. So let's start with it. They're all going to run together. It's hard to follow. So let's start first on the left one, and then they're going to restart. We'll look at. So the first one, is tight, very tight, SSD of 18 feet. The structure is pretty much touching, and the fire is moving really fast, very small. You see maybe spotting here and there. It's really the radiation, at least in this model, that's driving, just fire line just moving pretty much very systematically. And then I'll show in the next slide the fire spread rate, but that's how it worked in the first. Okay, so on the right one, that's the other extreme, right? It's gonna actually pick up slowly compared to what we just observed towards the left. So it's burning. Obviously, there are still not enough structures on fire to create enough fire spot, enough embers to cause ignition. And you also have less footprint of the buildings where the embers would land. So eventually you'll see, okay, now you see some embers landing. That's moving the fire line. You definitely see more embers in this case where the fire jumps. But again, you see the middle case already reached towards the end. This low density community is taking its time, and eventually the fire goes through. So there's no suppression action in SWIFT yet. That's why if the structures are close enough, there's enough embers, there's enough wind, eventually you get things burning down. So if I want to summarize what we just saw in the previous slide, this was the high density, this was the low density, medium density type of community. We are actually getting an average fire spread rate for that, given again all the everything else being similar, all the inputs, including the wind, which matched the trails community. And we actually calculated the average structure separation distance for the wish and go for trails community. And this is the fire spread rate that was observed and in that case, in the fire, versus our simulation, which was 330. So we're plotting actually 340, what was observed. So that relationship is not linear, and that's okay. But now we're getting to the point that we could use the model to establish some scientific reasoning for other than, again, just pure experiments for these either mitigation or response actions. So with that, in summary, I talked about, I started with, looking at the data, but moved to SWIFT, talked about a model that's developed to capture fire spread inside communities that account for structures as fuel and captures right now fire through radiation and spotting. It does incorporate uncertainties in several parameters, given the randomness in this process. And the model is computationally fast. It takes minutes to run these simulations, and it's relatively user-friendly. And the way we're hoping we would be able to use in future, we can use it for mitigation to identify vulnerable parts of the community. We could use for preparedness to optimize some resource allocation and guide where firefighting could happen, and could also use for response to decide if this fire, when it reaches that community, given the condition on the ground, it would be the emergency responders, they would be able to suppress or not based on the rate of fire spread. So everything is I presented this is all work of my students, and all the credit goes to them. So I've listed them here, and also the funding agencies for the project. They're acknowledged their support. So with that, I'll stop. Thank you very much, and looking forward for questions.
Okay, thank you very much, Nagar. And everyone, I want to join you in giving a hand for an excellent presentation. We do have a few questions already in the Q&A, and if folks that have questions can please add those to the Q&A. We'll go off of that. It's hard to track stuff in the chat, so we try to use Q&A, and I forgot to tell everyone that at the beginning. So we have a question here from Porfirio. The campfire and others, most of the structures were destroyed within hours from the ignition. And what temporal distance was evaluated from the ignition to the damaged structures?
I think the question, if I'm, let me, 1 second. I probably want to share my screen again, but this happens to me all the time. When I stop sharing, go back, my computer goes crazy, but I think you can see it, hopefully. Okay, it's back. See, I knew that would happen. Sorry, I have to do this manually. Okay, so I think the question refers to, if I understand correctly, because the campfire is located, it's included in this list. We're talking about the ignition versus the structure. So same approach as for all the structures for all the fires. So for campfire, the same thing in a sense that for a given dot, that would be a structure. We had the location of ignition for the campfire from, again, what's out there. And then we defined the centroid of the final perimeter to get the direction, and the separation distance per structure is defined as the distance between the structure and the ignition plus that perpendicular, but that distance to the line of the fire spread. So this point, if it's right here, that's so close to the ignition, it would be obviously way smaller. Let me add one point. We want to get to the other questions, but when we set this up with my student who's, well, now graduated, we talked about actually simulating all of these fires, you know, listed here, so that we would actually get the actual rate of fire spread. So we are trying to mimic how fast the fire would get to those structures, right? And it's not fair, perhaps that distance may not just reflect how fast the fire would get from the ignition to the location of structure, but the simulation tools, based on what we've observed and what we tried and a couple of cases that we had, there are still some errors in some of these fires compared to the, you know, the observations we get from, you know, ground truth, due to some simulations not having fire branding, some simulations have fire embers, but they don't have other mechanisms. So we ended up basically having just a proxy for that.
Okay. There are a couple of questions about changes in weather, and it appears that for now your model has a consistent weather input, and of course in real life the weather changes pretty constantly across these fires, and is, you know, do you feel like that's a big factor, and is there a way to actually integrate particularly changing winds over the course of these fires?
So the wind actually input changes per time step, every 5 minutes. So there is a raster input for the wind, again, one for mean wind speed, one for gust, and that is actually the values are different per time step, or it can be the same depending on whatever is the input. However, I want to expand on that, like knowing or explaining where we're going and thinking. The values are changing based on time, but not across this region, in the sense that all these cells right now, they're seeing the same wind. And the question, so we are actually looking into that effect. We are trying to connect, or let's put it this way, use the output of, you know, another model to get the wind field across this area, to see how that changes the output over if we change wind over space. But our original thinking, so I cannot confirm, I'm still not convinced that would be critical, because some of these WUI communities, it really depends on how we want to use this model. If we expand the area, the footprint that we are covering and we are modeling, then yes, that's needed. But if you're keeping the region to these smaller WUI communities, then that wind pattern across, we're not looking at kilometers, right? Then it probably doesn't change within the time frame we're looking at. So the change in time step. However, we are in the process of implementing that to see whether we need to keep it changing over space or not.
Okay. there are several questions, and I will admit I had this question as well, about the structures. Because of course, that's one of the major ways that on the mitigation side, there have been efforts towards making the WUI less flammable, is by actually changing the components of the structures, the siding, the roofing, all those sorts of things. So how much do you think that affects, and how are you incorporating different types of structure exteriors and components into your modeling?
That's another very good question. So it's in the process, but I think it's going to take us a little bit of time, because this is the way we're thinking and we're working on it. Whether it works, we'll probably know in a few months. We are using, so we have started some primary features, such as the roofing type, so Dean's data, we're relying on Dean's data has several, maybe 9 or 10 different features. It's too much to include all those features. Number one, because we don't have, again, robust information from Dean's data on how some of those features would, in terms of absolute value, would change. It's in terms of comparison, I think they give us some idea that, okay, feature A would help, but absolute values, in order to be included in the model, I don't think we have enough information on milder fires and less severe fires to be able to get a good gauge there. So number two, I would say, is that if we want the user to implement and use this, we probably don't have all those detailed informations if we use too many features to implement. Like, you say, okay, user A, here's the model, you can go ahead and use it. They're going to say, okay, for my community, I don't know all the window, if they're single or double window panes for all these, houses within the community. Maybe they don't still have that kind of information. Some of it, such as, again, roofing type, there's potential for, using satellite images, AI, these kind of things to extract the information from the user perspective to be able to. So selective features, we're working on them. And then the way that we would like to reflect is the ignition threshold. So embers land on roofs, then they cause ignition. But whether that roofing is, type A, type B, type C, whatever that is, that threshold is being adjusted in the code based on the type. So that's another comment. And then I think that's pretty much it. I think I'm missing something, but that might address some of the parts of the question.
It is a lot of complexity. I wonder if a simplified first pass at it is actually to just simply delineate between, since the DINS data are all in California, right? Mm-hmm. Whether or not the house was built before or after the 2007 WUI codes took effect, right?
Yes.
There's a simple starting point, but yes, a lot of complexity in there that always adds computational processing time to any sort of model. Let's see, another question that is related to structures is how difficult is it to actually input a community building footprint into the model? Is that something that has been fairly simple for you to do?
It's relatively simple, especially because the first code, so this is literally, I don't know if my students on the call or not, but he literally, finished this process earlier this week. We moved the code to, it was not in Python. We moved the code to Python to make it a little bit more, generalized. And in that process, we made the user interface for the initiating the process. We made it more streamlined so that you actually don't need to know too much to be able to work with the code, and then build the footprints. These cases that you saw here, we're using, some people call them Microsoft, you know, building footprints and so on. So we're relying on that database. But in terms of, you know, having a README at the beginning that you can get this information from here, here, and load it through to the code, we actually just recently tried to do that so that, you know, it's not just, you know, my research group who would be able to use it, but a general user would also be able to systematically and easily use it without knowing what's inside the code.
Right. Okay. Another question that is sort of related to the weather question that you answered earlier is about fuel moisture and whether or not fuel moisture content for the vegetation is being taken into account in your spread calculations.
That is a very good question. Simple answer is no at this stage. There is a long list of things that can be done to improve the model. And I know that that is important, but I think our primary focus, what's on top of the list, is mostly focused on the structures, and then we'll hopefully get to a little bit more advanced on the vegetation. I think right now we're putting much of our effort on improving, for example, what you mentioned, structure features. That's where the full focus is right now.
There's a very specific question from Alec in here about the NIST community types, the 3-part simulation based on those 3 NIST community types. Mm-hmm. And the question is, I don't remember seeing much green unburnt vegetation at all between the structure layouts of the 3 densities.
Yes.
And were your simulations just of structure only neighborhoods for those 3 runs, or is there any vegetation in there?
Very correct observation. Yes, we do have we had a series, but again, given the time frame, I wanted to stop at 45 minutes into the presentation. We have several of them, but indeed, yes, we do have versions where we have vegetation. The ones we are looking at right now, there are no vegetations. There are these, the simplified, just to keep it, I didn't want to get into too much. Yes, correct. There, but vegetation makes a difference, absolutely. But that becomes, you know, again, going back to the beginning, you know, defensible spaces, how much vegetation we have. So here, that's why the reason I'm showing this version is that I didn't want to mix up. It's like a built up. First this case, then what if we add vegetation, or, you know, trimming the vegetation, these things. So combined approaches to look at the effects. So here, purely the objective was to look at this SSD, effect of SSD.
And I think that we are 1 minute from 3 o'clock here, so I want to go ahead and wrap up. I guess the question that all of the potential users of this are asking is, okay, so this looks like a fantastic tool. When is it going to be available for users? And are we talking years and years away here? And really, how much money do you need to make this available, right?
Okay, that's not how. Should I think about it? I did not think. I thought that, you know, we'll just put it on, you know, our website or whatever for free, and then people can download and use it. Good question. I never thought about it.
that is the question for you to think about for future.
Honestly,
right?
The approach was that this would be available to the community, but maybe I should rethink that answer.
Well, grant funding, right? Grant funding. You got to think about grant funding. Okay, so thank you so much, Nagar. That was a fantastic presentation. Such, you know, we all know that WUI is where we have the problem. So it's so important for folks like yourself to be working on this type of research. Next week, two weeks in a row, we will have California Fire Science Seminar Series this month. And next week, our speakers will be Eric Knapp and Jana Vlakovic from, oh boy, okay, Jana's with UC Extension. I don't know where Eric is. Is he Forest Service still? Somebody, Stacy's nodding her head. Okay, here we go. So they will be joining us next week to talk more about structure ignition in the WUI and fires. And this is just such a really timely, I think, set of topics for us to be at this point in the summer as we all wait with bated breath to see what fire season will hold this year. So thank you to everyone for joining us today. Thank you again to Nagar for a fantastic presentation.
Thank you, Michael. Thank you, Stacey. Thank you, everybody, and thank the audience. Thank you so much.
And for our audience, this presentation was recorded and it will be available in some X number of days. And when it is available, Stacey will be sending out an email to everyone that has the link to our YouTube page that these recordings are all located at. So thank you again, and we look forward to seeing you all again next week.